Like I was on pace to qualify easily, and then I fell apart, and I just barely made it. I'll tell y'all that story some other time. Okay, here we go. If I have time at the end, I'll tell you. Okay, so we're breaking section 4.3 up into some pieces. So this is going to be 4.3a.
Hey, mama. Everybody, cool.
Okay, we've already talked a little bit about this idea of where a function's increasing and decreasing. Okay, so I'll just throw something up there. Doesn't really matter. But what do you know about the function from here to here?
It's increasing.
It's increasing, right? And what do you know about it from right here to here? It's decreasing. And what do you know about it from here to here? It's increasing, right? So talk to me calculus. Give me some calculus that goes along with this picture. Positive derivative? Negative derivative? Positive derivative? What's the derivative here and here? Zero, right? So when the derivative is zero, it has the potential to do what? Be a minimum or a maximum, right? Change direction, okay? So let's formally state that, I guess. Let F, yeah, that got all crushed together there. Let F be continuous on the closed interval AB and differentiable. Where would I say it's differentiable?
Everywhere.
No, on the open interval AB, right? Because we don't talk about a function being differentiable at its endpoints. So let F, let me fix that. That's really ugly.
Exactly. Just because it's ugly doesn't mean
Let F, that's not much better, be continuous on the closed interval AB and differentiable on open interval AB. Okay, so here's what we can say. If F prime is greater than 0 for all x on the open interval AB, then F is what? Increasing. On AB. Similarly, if F prime is less than 0 for all x on the open interval AB, yep, then F is decreasing.
Hey. It's pretty heavy stuff.
Yeah, pretty intense.
This is pretty extreme.
It's extreme.
It's not nearly as extreme as yesterday. That's what your parents said.
She said,
Parker said his parents said.
what? They said.
They said, we got an email from your calculus teacher and she seemed pissed.
My mom was talking
Oh my god, that cracks me up. If f prime of x equals 0 for all x on AB, yes, then f is a constant. Oh wait,
Eels.
this should have brackets.
She's out somewhere, isn't she?
Oh,
She's out somewhere, isn't she?
No.
She's home.
She's home.
What the heck? Willie, that's like that.
Okay, so let's look at an example problem and talk about some things that we might need to consider. Okay? Determine where y equals x to the fourth minus 10x squared plus 9 is increasing and decreasing. Determine where y equals x to the fourth minus 10x squared plus 9 is increasing and decreasing. Well, prior to calculus, what would you have to do in order to work that problem? Graph it. You'd have to look at a graph, right? But you have this wealth of new knowledge, okay, that will enable you to answer that question without graphing the function on a calculator. What do you propose I do? Yes?
Since that's kind of like a quadratic, could you possibly set up like negative b over 2a to find the vertex?
You can't, because on this it has more than
Well,
It
yeah.
has more than one, yeah. Okay, so yes, take the derivative. So, when in doubt, take the derivative. That becomes the motto of every class. Okay, so what is the derivative?
Minus 20.
Okay. Now what are you going to do with that? Okay, guess and check. Right, guessing and checking is not a terrible idea, but how would I even know where to start? Okay, find the critical values, right? Find the critical values of this thing. So let's set it equal to 0. And let's factor out a 4x.
Yeah, you're right.
X squared. Yeah, you're right.
You're right.
Correct.
You are correct.
Okay, so either 4x equals 0 or x squared minus 5 equals 0 if you're showing all the steps.
Perfect square.
So either x equals 0 or x equals what?
Plus or minus the square root.
Plus or minus the square root of 5. So what are all of these potentially? These are, yes, they are critical values and they are potential mins and maxes. They are potential mins and maxes. Okay? So what do you think now?
You plug it back in.
You plug in this value.
Well, if I plug in those values, what am I going to get?
Plug in.
Numbers.
I'm just going to get some numbers. Is it going to tell me anything? Okay, if I plug them in, I could maybe sketch a graph.
Could you like plug in a point that's like a little bit before or after?
Oh, there we go. Now that's a really good idea. Okay? So it's like I need to plug in values that are around these. So here's what we're going to do. We're going to create what we call a sign chart. And we're going to put 0, and we're going to put negative square root of 5, and we're going to put positive square root of 5 on there. And we're going to test numbers in these intervals, right? Okay, so what's a number bigger than square root of 5?
What?
Hold on.
What's wrong?
5.
Okay, so 3. Okay, so 3. Okay, so 3 is a number that I need for you to pay attention a little bit better. Okay, 3 is a number that is bigger than square root of 5, right? Okay, where is it that you want to test this value?
In the original. Wait, what?
Okay, in the derivative. Why? Ah, so then I know the slope, if it's positive or negative, right? Because if it's negative, then I would know that the function's doing what in that interval? Decreasing. If it's positive, I know it's increasing. Okay? So let's take 3. Here's my derivative, right?
Yes.
Either one of those. And a lot of times using the factored form is easier. Because all you need, you don't actually need the exact value. You just need the sign. I just need to know if it's positive or negative, right? So if I plug 3 in, this is a positive number, right? It's 12. And this is a positive number. It is 4. And a positive times a positive is a positive. So what is the function doing out here? It's increasing. So we're going to draw an arrow that shows that it is increasing. Okay, now what might you want to check?
2, 1.
Okay, 2, 1. Okay, all right, so I don't know, I'll do 1. So if I plug in 1, this is what kind of number? Positive, but this number is negative, so the whole thing is. No, I don't need the values. What have you just learned? That there's a minimum at x equals square root of 5. Okay? Alright, so what number do we need to plug in here? Negative 1. Okay, plug in negative 1. No, you can't just. Okay, so this number is what? Negative. This number is negative. Think, people, don't just say things. Okay? You're just like saying it because it sounds rhythmic. Okay? Actually think. Okay? This one's negative, this one's negative, so the whole thing is positive.
Why couldn't
Okay.
we assume that the other ones? So since we have the last one being positive, and I mean the one before that is negative or it's decreasing, so why can't we assume that the others, like the one before that, is increasing?
Because just because it's a critical value doesn't mean that it is a min or a max. It doesn't have to be one. We'll do an example. Okay, it just has the potential to be. It would if it's symmetric, okay, but it doesn't have to be.
So 0 a maximum?
Yes, so 0 is now, I can now determine that at x equals 0, I have a max. If you're on your phone, get off your phone. Yes.
On like a y equals x cubed, is
Yes.
there something to call the origin?
Yes.
Would that be a critical value? Or would that
It will show up as a critical value, okay? But so that's what I'm talking about, okay? So here's what, I know we haven't finished this problem, okay? It's good that you're asking questions. Okay, so the question was, here's x cubed, right? The derivative here is 0. But what's the function doing here? Increasing. What's it doing here? Increasing. Okay? So that's not a min or a max. Austin said, so what's that called? He asked, is it a point of inflection? It is a point of inflection. And this is the next lesson. Okay? So, but this kind of goes hand in hand with your question, Nick.
Yeah.
Okay, so let's go back to this one because we still haven't tested this interval. -3, okay? So if I plug in a -3 right here, this term is negative, but this term is positive, so altogether it's negative.
Yeah.
Okay, so the question said determine where that function is increasing and decreasing, okay? This sign chart is not enough. You have to summarize the findings of your sign chart, okay? Yes, it makes sense, and AP used to actually take this as an answer to the question, but now they don't, right? So now we have to do, we just have to say, okay, I'm decreasing on what interval? I'm decreasing from negative infinity to negative square root of 5 and 0 to square root of 5. Because,
They'll always be open intervals, right?
say again,
They'll always be
yes, they will always be open intervals. Because what? Y prime is less than 0. And it is increasing where?
Negative 5 to 0.
Negative square root of 5 to 0. And
Square root of 5 to
square root of 5 to infinity, because y prime is greater than 0. Okay, so I'm just going to go back and kind of summarize what we did here. These are potential mins and maxes, you told me. And so over here, I create a sign chart. Using the critical values. I test values of x in the intervals on the sign chart. Where do I test them? In the derivative equation. Okay, so now from our sign chart.
Is this all like answer?
No, this isn't part of the answer. I'm still just kind of summarizing. Actually, we're kind of moving on to the next thing. From our sign chart, we can now determine what? Mins and maxes, right? So from our sign chart, we can determine mins, maxes, by finding what?
Slope.
Like,
By finding whether the function is increasing or decreasing around those values, right? So, in other words, by finding where the derivative, what does the derivative have to do in order for it to be a min or max? It has to change sign, right? Where the derivative changes sign.
So those would be like local.
They would be. Those would be local mins and maxes. We couldn't determine anything absolute because we're not on a closed interval. Okay, so if sign changes from positive to negative, what do we have? A maximum, right? If the sign changes from being positive to negative, we have a max. Right, if the sign changes from negative to positive, like this, negative to positive, then we know we have a min.
Because when I get home,
So on this particular problem, guys, Where is there a max?
Zero.
At 0, how do you find the y value of the max? You plug it into the original, right? So at 0, f of 0, right? So if you go back to this problem, right, so there is a max at 0, 9. How many mins are there? There's 2. And they are located where? Plus or minus the square root of 5, comma, f of plus or minus square root of 5. These signs are what? I'm sorry, not the signs. The exponents are even. So it will be the same, won't it?
Yep.
Okay. So it will be, let's see, plus or minus the square root of 5. If I plug that into the fourth, I'm going to have what? 25 minus 50, which is negative 25, plus 9, which is negative 16.
Wait, are you saying about the even exponents?
Since the exponents are even, you don't have to actually test both of these. It'll be it'll give you the same value. Because if the negative one, if you raise it to an even power, it's going to turn positive.
Okay. Okay.
But I mean, you could plug them both in if you want. So there's 2 minimums, right? There's a minimum at, if you're having trouble, there's a minimum at square root of 5, negative 16, and at negative square root of 5, negative 16. Okay, so all of this leads us to something called the first derivative test. Okay, and the first derivative test, it really, I mean, it says the same things that you guys have been telling me. At a critical value C. If f prime changes from positive to negative, if you have this critical value C and f prime changes from positive to negative there, then what can you tell me?
There will be a max value.
There is a max at C, f of C. Does that make sense to everybody? So what sentence goes next? If f prime changes from negative to positive, how do we finish that sentence? Yep. There is a min at C, f of C.
That's not any different from the other two units, right?
Say again.
Is that any different from the other two units?
The other.
Up there?
No, we're just summarizing it like in its actual test form, a little bit more formally. Okay, and then the last thing that I need to write here, what's the other possibility? F prime what? If it, not if f prime is 0, if f prime doesn't change sign at C. There's no sign change. It's like that cubic thing I drew, right? It was positive and it was positive. Then all I can say right now is then there is no min or max there. Pretty powerful
Oh my
stuff.
gosh, no means.
Well, there is both even
So what exactly
There's
could
no
we use
relation
a
like to this.
point of inflection for? Are we gonna go over that?
We are. Yeah, we're just not there yet.
Okay, I thought you meant after you want.
No.
Okay. Okay, I thought you were thinking like once you
No.
Exactly.
No. There's no pepperoni.
Today?
I like exactly.
Okay, so I'm gonna do one with you. Let's do one more together. What time is it? What? 1:52. Okay.
What's your dance plugs?
Were you ready? Oh,
He's a smart person.
Okay, apply the first derivative test. Yeah, this is an example, sorry. Apply the first derivative test to identify,
Oh, no, we're having the conversation.
apply derivative, oh, sorry.
I didn't mean
Test.
anything bad against your mother.
I didn't even hear what you said.
I'm sure she's lovely.
Apply the first derivative test to all relative extrema. Derivative test to identify all relative extrema. And here's the problem. First derivative test to identify all relative extrema. Okay? In other words, I'm looking for what? Mins and maxes, right? I'm looking for mins and maxes. So what do you think the first thing I need to do is? Find the derivative. What are you going to have to use? The quotient rule, right? So low D high, which is minus high D low. D low is what? 1.
And then just do you want us to distribute the negative?
Yeah, you gotta clean this thing up. This is way too hard to do anything with. Okay, so let's square this binomial. Okay, 2x squared. My inner term is 2x. My outer term is minus 2x. So that what goes away, right? So 2x squared minus 2.
Would you want to square that?
And then I have to do what with this? So minus x squared plus 2x minus 1 all over x plus 1 squared. Okay, so let's clean up. X squared. Y'all stop. Just stop for a little bit. Like, people can't even concentrate because you won't shut your mouth. Okay, so this is x squared, then what? Plus 2x minus 3 all over x plus 1 squared. Mhm.
Would it be wrong to think since that negative, because the trinomial in the numerator is x minus 2 squared, or x minus 1 squared, sorry, and that negative x, you can't change it to x plus 1 squared by chance?
I don't know what you're
No,
saying.
you can't.
Sorry.
The x squared minus 2x
You
plus
can't do
1,
that.
Yeah,
if you factor that out, it's x minus 1 squared,
right?
and it's a negative, so it wouldn't be x plus 1 squared, just because you have to apply the negative to the x, or?
You would have to square it before you could distribute the binomial
Okay.
because of order of operations, right?
Mm-hmm.
Okay, you'd have to have it squared first. Okay, so here's my derivative, right? Here's f prime of x. What do I need to find out about this derivative? Where it's 0 or undefined, right? I've got to know those two things, where it is 0 or where it is undefined. So it's 0 when the top is 0. It would be undefined where the bottom is 0, right? So the derivative does not exist when what?
Negative 1.
Okay, so x equal, okay, well, I mean, we can write that, I guess, if you want. So x equals negative 1, right? And then I need to figure out when the top is equal to 0, right?
Plus or minus 1.
So this is going to be x plus 3, x minus 1. So x is either equal to
Plus or minus 1.
negative 3. I don't know what you're saying, Austin, or x equals 1.
No, plus or minus.
Oh, okay, okay, that's fine. Okay, so what are these three values? They're critical values. What do I need to do with them? Put them on a sign chart. And then what do I need to do?
Plug in values around into the derivative.
I need to test values around them, right? Now, I heard somebody say plug those numbers into the derivative. If I plug those numbers into the derivative, what am I going to get? 0, right? I mean, that's what I just did, okay? So I need to test values around these in my derivative, okay? So yeah, well, I'm going to start out here. Let's do negative 4, okay? If I do negative 4, that would give me, well, the bottom's always going to be what? Positive, right? The bottom will always be positive. So I'll do this. That's going to be positive. If I plug in negative 4, this is 16 minus 8, which is 8, minus 3, which is a positive. So over here, the function is increasing. Okay, let's try negative 2. Okay, so if I plug negative 2 in right here, I get 4 minus 4 minus 3. So that's a negative over a positive. So this is decreasing. So yes, I've just figured out that at x equals negative 3, I have a max, right? Okay, what number do you want to try here? 0. Okay, so if I plug 0, remember I'm substituting into the derivative, I get a negative over a positive. So this is still decreasing. We don't know yet, okay? Okay, and then if I get over here outside of 1, a number bigger than 1, 2, you want to pick easy things, okay? So this is 4 plus 4 minus 3 is a positive divided by a positive, okay? So I now know I have a max at negative 3, f of negative 3, right? And I can figure that out. It's going to be 9 plus 6 is 15, plus 1 is 16.
Isn't it 9 minus 6?
It's a negative times a negative. It's plus 6, right? Where do you plug these values in? The original. That's why I wrote f of negative 3. Oh, I'm sorry. I'm sorry. Here, this is what we're plugging into, right? So it's 9 plus 6 plus 1 over negative 2, right? So negative 3, negative 8.
Something like that.
And that's your max. And then what else can I say? I've got a min at 1 f of 1. So that's going to be 1, what is that? 1 minus 2 plus 1, that's 0. Right? So just 0. Okay. Okay, so what did I tell you the other day is our first big application of derivatives? The thing we want to be able to do with them.
Oh.
Use them to sketch graphs,
Oh.
right?
Yeah.
I told you that was going to be our first application, was using them to learn to sketch graphs. So you could sketch an okay graph right now, but you're going to be way better at them because you're going to be able to find points of inflection and other values that will make it even better. Okay? But this is your first derivative test, and that's what you would do with it. Okay, so here is homework. What time is it?
3.
Oh, 3.
It's too late.
It's been a minute. Since he came home. Who is Robert? What do you say to him?
Okay, so you are going to do, there's a worksheet here. There's 2 worksheets here. We're just doing the first one.
Is there any book work?
There's no book work. Yes, sir. Remember these are
Worksheet 1 home. Worksheet 1 or you take it.
Yes. Okay, so in this that I just handed you, it's 2 pages stapled together. You don't have to worry about the back page. If you look right here, it's just my handwritten page, and it's 1 through 9. Okay? And you guys have a good weekend.
We